Good morning, good afternoon, and good evening, everyone. Welcome to the OpenFOAM and the Combustion Simulation webinar. So here I'm very pleased to introduce our speaker today, Professor Shuo Yang from University of Minnesota. Okay, so the title of today's presentation is Modeling of Multiphase and Reacting Flows in OpenFOAM. High pressure phase change and the plasma assisted ignition. So before the presentation, please allow me to introduce Professor Shuo Yang first. Professor Shuo Yang is the Richard and Barbara Nielsen Assistant Professor of Mechanical Engineering at the University of Minnesota, Twin Cities. During 2017 and 2018, Professor Yang was a postdoc research associate in mechanical and aerospace engineering in Princeton University. He received his PhD in 2017 and a master degree in 2014 in aerospace engineering and another master degree in computational science and engineering, all from Georgia Institute of Technology. He received a bachelor degree in mathematics and applied mathematics from Zhejiang University in China in 2011. Professor Yang's research focuses on the modeling and the simulation of laminar and turbulent reacting flows, including combustion, plasma, particulate, and multiphase flows, as well as hypersonic aerodynamics. He has authored for more than 50 peer-reviewed journal articles and conference papers in which he received the editor's pick and featured article awards from Physics of Fluids and Combustion and Flame. Professor Yang is a recipient of the DARPA Young Faculty Award and the ONR Young Investigate Award. His research is supported by NSF, ARL, ARO, DARPA, ONR, and ARPAE from United States. Professor Yang is a senior member of ARAA and a committee member of 3 ARAA technical committees. Professor Yang also serves as an active reviewer for many top-tier journals for which he received 3 outstanding review awards. Okay, so Professor Yang, now I give the time to you. And after the talk, we will have the Q&A session to discuss the questions from the audience. Thank you very much.
Thanks, Professor Zhang, for the nice introduction. Hello, everyone. Thanks for coming to my talk. So today I'm going to talk about some multi-physics modeling in OpenFOAM, specifically 2 topics. One is about high pressure phase change. The other one is about plasma assisted ignition. So the talk might be a little bit long because I try to cover both. So first, why do we want a high pressure? Because for propulsion and power system, we want high efficiency and high energy density. Why high pressure can provide both? So if you look at the diesel engine cycle, the output work can be considered from the area within this cycle. And if you, for the same amount of energy input, if you increase the pressure, you can basically have more output work, which means you have a higher efficiency. For gas turbine Brayton cycle, here we have 2 cycles which give the same output work. But if you increase the pressure doing this way, you can use less input energy to achieve the same output work, which also means high efficiency. And recent years, another very hot topic is the detonation engine, and with a very special cycle, it can give you more outwork using the same energy input. So anyway, in any of the engine, if you want high efficiency, you need a high pressure. High pressure also means high energy density. This is relatively easier to understand. And here is an example. If you want to give 10 megawatts power, and if you use the low energy density steam power turbine, then this is the size you need. And this is a human being size. But if you use a supercritical CO2 gas turbine, you can reduce the size of the engine to this small, which is probably even suitable for onboard flight. So you can see this can reduce a lot of material, can make the engine lighter, and a lot of benefits. Okay. As a very extreme example, that's a rocket engine. We know that a rocket engine needs a lot of power. And if you do not do high power density, then you need a huge engine, which is very heavy, need a lot of material, and it's impossible to push it up to the space. So all the rocket engine operate in very, very high pressure, something like this. Okay, and during my PhD, we did some simulation to mimic the condition in such cases. And when you have a high pressure, some new concept introduced, that's so-called supercritical fluid. And this is a figure I copied from Wikipedia, and it's essentially a single component CO2 phase diagram. And you can see this is the triple point, and this is the triple point is the 3 phase come together. If you go in higher, follow the boundary between the liquid and gas, eventually you reach some point called the critical point. And above the critical point, the liquid and gas phase, you cannot tell the difference. They kind of become similar thing. This is so-called supercritical state. People still try to give a rough boundary between liquid-like and gas-like, even in the supercritical region. That's so-called Widom line, which you can join like here. Okay, and traditionally, historically, the so-called term transcritical was defined as transition or crossing the Widom line. So if you have transition between these two regions, the liquid-like and the gas-like, you call it transcritical. So transcritical essentially is a special scenario of a supercritical. Okay, so that's what the academic community accept, which I don't like this definition for transcritical. Because if you think about the English, if we say transcritical, if you don't know what the community, how the community defined, how would you define it? You will say transcritical should be between subcritical and supercritical, right? So that's the definition I prefer. Unfortunately, no one accepted it because the terminology has already been used. So I have to say we wanted to handle transition between subcritical and supercritical rather than using transcritical, unfortunately. Another thing I want to mention is the multi-component situation is very different from single component. Single component is like this. Multi-component in the subcritical region, you introduce another thing called two-phase zone rather than just a line. So this is very different. And this is just one example. If you change the condition or change the composition, this dome can have very different shape. Later you will see some examples. Okay, so rocket engine, actually you don't need to worry too much. Rocket engine, the pressure is very, very high. Typically, it's always supercritical. You don't need to worry about the transition between super and subcritical. But, so we are talking about something else. The first example is the gas turbine jet engines. Over the past half a century, the jet engine development has pushed it towards higher and higher pressure, as you can see from this figure, for both the military engine and the commercial engine. And nowadays, if you look at the military one, all of them are within this region. This region is when you have a supercritical liquid-like fuel injected into subcritical gas air. So as you can imagine, you will inevitably go through a transition between supercritical and subcritical because you mix these two together. And if you want to really accurately simulate such thing, you need one framework which can handle all the thermodynamic regions, not just say I can only handle supercritical or I can only handle subcritical. That's not okay. You need to handle all of them together in one framework. If you look at the commercial one, this is a supercritical liquid-like fuel injected into supercritical gas-like air. Looks like similar to rocket engine. Maybe we don't need to worry about the subcritical or transition. Everything looks like just in the supercritical region. But is that the case? So I give you an example. This is not exactly the composition in the jet engine, but just an easy example for you. When you mix two supercritical fluids together, will the mixture still be supercritical? The answer is not necessarily. You might go back to subcritical again. The reason is the true critical point could be much higher than each single component. And so when you mix them together, you raise the critical point, and suddenly your condition becomes subcritical and in the two-phase zone. And that can give you the so-called phase separation. And one interesting phenomenon many people talk is so-called retrograde condensation. So here is the example. You start from point A, you compress the system to get high pressure, then first you get a phase separation here. You go inside the two-phase zone, you have the condensation. But if you compress it further, it go outside again and become gas-like again. So that's the so-called retrograde condensation. Okay. Okay, so the most important observation I want to say here is a subcritical two-phase zone can be mistakenly recognized as a supercritical state. If you use the traditional approach, what is traditional approach? I mean the traditional approach for supercritical fluids. That's the so-called dense fluid method. Dense fluid method, basically the only thing you need to do is change the equation of state, change the ideal equation of state by the real fluid equation state, and also change the transport property by the corresponding real fluid one. And in those formulations, you will need a critical point to evaluate many functions. And in the traditional method, what people do is so-called pseudo-critical point. Pseudo-critical point is a simple kind of a linear model to predict the mixture critical point. What they do, for example, if you use a linear model, the mixture critical point you will predict is here. The true one is here. So you can see it's very different. Okay. So we need this is one example. The other example may be interesting to many of you is the liquid fueled RDE. This is actually an even better example. It have more transcritical phase change. The reason is the residence time are extremely short because the detonation wave is extremely fast. So even though detonation give you very high temperature in the chamber, the time is so short, not enough for the droplet to fully evaporate. So you will have detonation wave collide with the shock. And the later example I will show you, not just the shock will collide with the droplet. The shock will not completely destroy the droplet or fully evaporate them. Very likely the droplet can survive to the reaction zone. And if that's the case, all these things also can be coupled with the reaction as well. And another reason I said liquid fuel RDE might be an even better example is it have extremely large pressure and temperature variation. For example, this is a recent news I heard from some friends doing MD. They indicated that detonation triple point might have extremely high temperature like 9,000 K or 2,000 bar. On the other hand, the many region of the chamber is a very low pressure, very low temp, and relatively low temperature in the near the injection. So you have a very large variation. of PNT. And so this is the phase change. You will have subcritical, you will have supercritical, you will have transition, you will have phase change. You need one framework to handle all of them. And so in our work, we can do that in one framework by the so-called vapor-liquid equilibrium, VLE theorem. Okay, so what is VLE? VLE is the foundation of everything we talk about the high pressure phase change. And the most fundamental VLE solver is the so-called TPM flash. And how this name come from? TPM flash is to, you have a given temperature, which is T, you have a given pressure, which is P, and you have a given composition, which is N. If all these are given, you can calculate the equilibrium, the phase composition. How to calculate that? First, we rely on the real fluid equation of states, but we do this for each phase. We do not do a mixture between the, we do not do a lump together the EOS. We do this for each phase. And based on, we use Poon-Robinson EOS. Based on this EOS, we can derive very long formula for fugacity, and you can find a formula in our paper. Fugacity and the fugacity equation, which is this, is essentially the so-called VLE, vapor-liquid equilibrium. And you can look at how fugacity equation look like. Very simple, right? So basically, for each component, its liquid phase fugacity should be balanced by its gas phase fugacity. And that's essentially vapor-liquid equilibrium by its naming, right? And how to understand that? Fugacity, some of you may be familiar with it, some of you not that familiar with. You can consider it as an effective partial pressure. When you have ideal gas, this is exactly partial pressure, but when you have a real fluid, it's effective partial pressure. And this is basically said that the effective partial pressure of the two phases balance each other for each component. Fugacity can also be understood as a measurement of chemical potential and the Gibbs free energy. And you can do a derivation to find that this is equivalent to give a local minimalization of Gibbs free energy. That's why we said VLE is first principle from the first principle thermodynamic laws. It's not, I don't like to call it a model actually. In addition to these equations, the other equation we need to use is so-called Rutherford-Rice equation. And this is not described by any special physics, it's just derived from some definition. So ZI is the so-called overall feed mole fraction. You can consider it's the overall mole fraction regardless of what phase. And by definition, it's the gas phase mole fraction multiplied by the mole fraction of this component within gas plus the mole fraction of liquid phase multiplied by the mole fraction of this component in liquid phase. So very natural definition. And this equation together with just summation of yi should be 1, summation of xi should be 1, and then you can derive this equation. Okay, so these are the governing equation. And in the real VLE solver, the solver flow chart looks like this. First, you need to have an initial gas of this equilibrium constant for each component. And there are many ways to do that. You can use Wilson equation or TPD or a combination of them. So that's, I don't put details here. Those are in the paper. And then based on this, you can solve the Rutherford-Rice equation to get your phase mole fraction. And then you can have these two equations to get your xi, yi, which are mole fraction gas, mole fraction in liquid. And then you can use the Poon-Robinson EOS to determine your fugacity for each component for each phase. Now you can check whether you reach the VLE. If you not reach the VLE, you need to adjust your equilibrium constant and going back, so on and so on until this loop converge. You find a solution. Once you find a solution, you can update all the thermodynamic property because this solution determines all the thermodynamic property. Okay, so a natural question people have is, the series name is VLE. It has the name of equilibrium, but is the equilibrium assumption okay? CFD cannot tell you the answer, so we need to look into MD. I learned the figure from Professor Li Chao's paper from Purdue. So you can see the non-equilibrium process basically will cover this, say, for example, the disappear of the surface tension and the transition for the evaporation. And you can see in such condition, typically is 1 nanosecond or several nanoseconds. This is much smaller than most of the CFD time step size you will use. For this reason, the non-equilibrium effect is negligible, and the VLE should be valid. And as a result, the phase change is dominated by the slower diffusion process. This is actually also the case for the, if you remember, those low pressure phase change model is like this as well. Okay, so now we have the solver. Let's look at some examples, and we can use the TPM flash to predict the phase diagram for many mixtures. Here is an example adding small amount of water to CO2 methane mixture to mimic the SCO₂ system. And you see, when you only have CO2 and the methane, the peak pressure is the critical pressure will be less than 100 bar. But if you add only 1%, you see how much the critical pressure being pushed up, and you can go inside the operating condition of SCO₂ system. If you give even more, you have a lot of overlapping. You will have a lot of two-phase zone and phase separation. We know that theoretically all the thermodynamic and the transport property, they are function of a critical point. So to get a true critical point should be very important. But let's take a look exactly how important they are. Here I use the CP as an example for you. You see this one with VLE, this one without VLE. You can see in certain region, yes, it probably doesn't matter. That's why a lot of paper in the literature, you can find they didn't use our way, they use traditional way, still okay. But near the critical point, near the dome region, you can see they are very different. Okay. Okay, so now I want to introduce a second VLE solver, which is HPN flash. And TPN flash, which we already introduced, that's the foundation of all the VLE solver. All other VLE solver essentially built upon them. HPN flash, by its name, is a given enthalpy, pressure, and the composition, rather than given temperature, pressure, and the composition. That's why it's called HPN. And how to solve HPN flash is essentially solve TPN flash, but you don't have a T fixed, so you guess a T, and then solve TPN flash, and then you try to see whether the results can match your given enthalpy. If not match, you update the T, and so on and so on. Eventually, you get the equilibrium solution for HPN. Okay, so roughly speaking, like that. Why do we need so many different VLE solver? The reason is we are not just interested in thermodynamics, right? We're interested in CFD. So to do CFD, here's the thing. This is a development we did based on row pimple form. It's a low Mach solver, but it has the transonic extension to allow it simulate the transonic condition as well. So you can see in typical CFD solver, what you will solve is energy equation or enthalpy equation, rather than temperature. Temperature is not what you directly get. So naturally, you need HPN flash rather than TPN flash. So you give the enthalpy or energy, let the HPN flash tell you what the temperature should be. And the TPN flash is as a part of the HPN flash. So you can see there's many loops in the solver. Okay, so I want to emphasize the CFD solver based on HPN flash doesn't mean enthalpy, doesn't mean isentropic. Isentropic is when this is fixed, but we use HPN simply because we solve the energy or enthalpy equation. We know the value, and then we use HPN to provide the local instantaneous thermodynamics. It doesn't mean we enforce the process to be constant enthalpy. So that's something many people get confused, or even the review. So I want to remind here. Okay. So now we can see some examples. We use this CFD solver first to test SCO₂ shock tube. Okay, so you will have a shock wave going right-hand side and expansion wave going left-hand side. What we found is for the shock wave part, the VLE didn't make much difference, but for the expansion wave side, you can see clear difference between the with and without VLE. Okay, and if you look at this, how much phase change we have? It's just from 1 to it's about say 10% or a little bit more than that. We don't have a lot of phase change, just a little bit, but this already make the density very different. You see the density and the with and without VLE become very different. And this is essentially because we have a partial condensation after the expansion wave. You trigger the phase change, you trigger the latent heat, so it also changes the temperature. Okay, so the point I want to make here is even small, very small amount of phase change can have significant impact on the, say, density or other quantities. So it's not negligible at all. Okay, and then we try to mimic the real SCO₂ system. So we do this Jet-in-crossflows simulation. And essentially in SCO₂ system, you have a CO2 with a little bit impurity water comes in, and you can inject the methane or oxygen depending on which injector you are talking about. Okay. And we can do a parametric study. And the major effect is the lower the temperature, the more phase separation you have. Phase separation, why I want to say phase separation here, because the inflow is gas phase, is supercritical gas-like, and the injection is also gas. But when they mix together, they trigger condensation, because you raise the critical point, you have the two-phase zone, you have phase separation. And the lower the temperature, the more phase separation happen. The higher the temperature, the less phase separation happen. And it also depends on which species you inject. The oxygen have a higher molecular weight, so the jet bend less, and it also have more breakup due to its higher density. Okay. To do more analysis, we can project the CFD data into the thermodynamic regime diagram to see more information. For your reference, I also put the isentropic line for all the cases here, just to show you, although we use the PHN flash, the solution is not following isentropic line, because we are not enforce constant enthalpy. We just use it for the convenience of CFD. And you can see a lot of scattering, and the finding is the higher the temperature or more breakup, the oxygen have more breakup, you have more scattering of the point, and more thermal conduction. And the more thermal conduction will make you further away from isentropic line. As you can see, this one is away a lot, and while this one is pretty close. Okay, and if you compare this figure with the last slides, you can see that this is 20% water in the composition, this is 10%. When you have less water in the composition, you have less phase separation. That's as expected. And the different amount of water in the background flow can actually change your phase boundary, such that for the same trajectory, some give you phase separation, some does not, depending on the phase boundary. Here is the due line. Okay, So that's the example about the SCO₂ system. Now we want to talk about the code performance. Taking this 1D shock tube as an example, if we run ideal gas, we take about 4 seconds to finish the case. If we do real fluid EOS plus VLE, you need 162 seconds, so 40 times slower. And for this reason, the state-of-art VLE-based CFD can only handle 2 components. In all the literature we found, everyone is just doing 2 components. No one doing more than 2 components until very recently. I will mention that. So what's the solution? A natural idea is, can we tabulate the VLE solution rather than on the fly calculate VLE solution all the time? But the thing is, in the real mixture, you will have a lot of components, and the dimension of the tabulation will increase sharply with the number of components. So for example, if you have just 4 components, you will have a 1.9 terabyte table, which is impossible for any memory in the HPC. So a natural idea, because we from the combustion community, we are very familiar with the ISAT idea, which people use to do the finite rate chemistry. Now, why not? Why don't we also apply it for VLE calculation? So we can dynamically construct some table, and we only do calculation when necessary. We want to avoid all the repeated calculation. So we apply the ISAT to PHN flash solution, and in the ISAT you have a mapping, and the X in for VLE solution is pressure, enthalpy, and composition. That's the PHN, and the output is temperature and the say density and the phase mole fraction. And in the VLE, in the ISAT, a record in the table, you need to have X0, Y0, and a gradient. Gradient you can evaluate numerically, and you can also evaluate analytically. We learned the derivation from Thresh-Mannon's group. They did a lot of derivation for the how to do analytic evaluation for the gradients in VLE solution. And in the VLE, in the ISAT, you basically build this so-called either ellipsoid or region of accuracy, and any point lost into this region, you can do linear interpolation to get the value rather than do a on-the-fly calculation. And you store all the data in a binary tree like this. Okay, so ISAT can save a lot of calculation of VLE on the fly. And this is just more information about ISAT. Some of you may be already very familiar with it. If the new point directly lost into the region of accuracy, you can do the linear interpolation. And if a new point is outside it, but you find the accuracy of linear interpolation is actually good, then you can grow your ellipsoid. And if both are not the case, you need another VLE calculation. You add another ellipsoid. That's how it works. Okay, so apparently the threshold matters, right? So here we show some example. If you have a too large threshold, you will introduce errors. But if you have small enough, you will get very accurate result. So to consider both the accuracy, you want acceptable accuracy and also fast enough speed. Here is what we get. So we can get 40 seconds for the case. And if you do analytic one, you can save a little bit better. So together we get 14 times speed up. So by this way, we can handle more than 2 components by VLE-based CFD. And here is the example case we did. It's 3 components. I think this is the very first 3 components because we never see it in the literature, and we can do it pretty fast. But I want to mention, recently there's another paper published on the POF, and they did 5 components. So we are not the only one doing more than 2 components now. There are also other groups. Okay. Okay, so that's the all the previous results was from the low Mach solver, and for other applications like detonation, you can have more than Mach 5 and definitely cannot use that solver. So recently, we also coupled the VLE with the fully compressed solver based on the row central form. And the row central form used the central upwind. And in addition to couple the VLE, another thing is for fully compressed solver, if you do supercritical or transcritical, you will have a spurious pressure oscillation. But there's already some method to handle that. For example, this double flux model. So we also coded this up together with the VLE. And an example case we are doing now is not yet detonation. We just want to look into a simple case first. That's a shock droplet injection, like this. So this is the simple case we just simulated very recently. And so basically when the shock collide with the droplet, you will raise the pressure and you push the condition from subcritical to supercritical. It's not directly visible from just a vapor fraction, but you can probe the data here and map that into the thermodynamic regime diagram. You can tell whether it's supercritical or subcritical. Another thing is you have a reflection wave, which will trigger a high temperature, high pressure region here. And this is the major region for the evaporation. Okay. And we try to see how much evaporation actually happened. So simple way to do that is you do a VLE solution, you do another CFD without a VLE. And you can see the difference is only 6%. So that means the shock wave is probably too fast for significant phase change. It collide, it's move away, is too fast. So phase change is a little bit slower. So only this amount happened. But that's not a bad, scientifically, that's not a bad news. That means very likely the droplet can reach, if it's a detonation, the droplet is likely to reach the reaction zone. That means you will have a VLE interaction directly with the reaction zone. That scientifically, that's more interesting, and we do plan to investigate that. Okay, so that's the first half of my talk about high pressure phase change. To save time, let's go to the next one about plasma assisted ignition. Okay, so the first project, a recent project we did is about ammonia combustion, plasma assisted ammonia combustion. Why we want ammonia? Because it's carbon free, and it can give clean, it's likely to give the clean combustion. Ammonia can be renewable, and it's indeed carbon free. Traditional ammonia synthesis is by the Haber-Bosch process, which is not renewable, and you actually need a lot of machine to do that. That's the major way nowadays. But today, a lot of new methods come out. You can even just use air and water to synthesize ammonia using renewable energy like solar or wind energy. And the energy density of ammonia is pretty nice. It's similar to the gasoline one. It's like half, but not order of magnitude difference. You know, like the battery is order of magnitude lower than gasoline, but ammonia is pretty nice. And it's effective hydrogen carrier, and it's safer and easier to store or transport than hydrogen. But ammonia have many disadvantages. So its flame stability is very bad. You can very easily get limb blowout. It has very narrow ignition range. It's very hard to ignite ammonia, and it gives you a lot of NOx. And recently, Professor Wintinson's group in Georgia Tech did this experiment. They found they basically add a plasma to this swirling combustor. They found that they can extend the limb blowout limit for ammonia flame. They can also make the ignition easier. And most surprisingly, they found Even NOx can get reduced by plasma. That's a surprise. Why is a surprise? Because normally for other fuels, plasma will increase NOx. Plasma will enhance the oxidation of nitrogen to increase NOx. But for ammonia, somehow it reduces NOx. The thing is, experiment can observe it, but cannot tell you why. So the job comes to my group. We will eventually simulate their device, but to do parametric study, let's start with a 0D simulation. So 0D simulation is very simple. Basically couple the ZD plaskin to simulate the nanosecond discharge and use ChemKin to simulate the gap between the discharge pulses. This is exactly the same as what Professor Zhen Chen did group did before. And the ChemKin part everyone's familiar with. The ZD plaskin part, you still have species equation, but for plasma species. And this is the energy equation. And you want to know how much heating this plasma give you. So you have the external enforced power, and you want to calculate how much of this goes into the plasma chemistry, how much of this goes to accelerate electrons, and the remaining can become heat. So that's how the ZD plaskin work. Okay, so we use this tool to simulate, do parametric study for plasma assisted ammonia combustion. And indeed, we find the same observation as the experiment. We have faster ignition and lower NOx. Faster ignition is as expected. You see, we get order of magnitude faster ignition. And this was one of the original motivation for PAC, is to make the scramjet ignition easy. And one interesting I want to say here is plasma is not the only way to give fast ignition. If you can do the same high frequency pulse, but using laser, you can give a pretty similar fast ignition. But the traditional spark ignition will give you much, much slower ignition. On the NOx side, the story is different. Only plasma can reduce NOx. The laser ignition gives exactly the same amount of NOx as the spark ignition, no benefit. Okay, so simulation can give us all the information, so we try to understand what's going on. For ignition, it's quite easy to understand, just like hydrocarbons. So plasma can give you much faster generation of OH radicals. Laser can do much faster than spark, but is much lower than plasma, because in the laser, all the energy go to thermal energy. In plasma, significant portion go to chemistry. And O1D is a very active, excited states of the O radicals. And apparently spark ignition will not give you any O1D. Laser can give you a little bit, but plasma is the major one, can give you O1D. The reaction is the electron plus oxygen give you O plus O1D. O radicals similar to OH, as you can see, the performance. So it's very easy to understand why plasma give you faster ignition and why laser can also give you faster ignition. Both are much faster than spark. And if we look at the path flux diagram, we can see one big difference is for plasma, the major generation of OH come from O1D, while for laser and spark, it's all come from O. The reason is the major reaction E plus O2 become O plus O1D is not there in laser or spark because there's no electron in these two. Okay. So now let's look at NOx reduction. Why we have NOx reduction? So so during the pulse, the path flux analysis looks like this. You can see the plasma case actually push everything towards nitrogen. So plasma essentially reform the NH3 to NH2 to eventually nitrogen and hydrogen. Laser and spark, they mainly will still push it towards NOx. And in addition, they are actually not very active, not very reactive during the pulse. So what you can see is the total amount of ammonia is almost constant for laser and spark, but drops significantly for plasma because plasma reform into nitrogen and hydrogen. So when you get ignition, the plasma case already have very limited amount of ammonia. So the amount can go to NOx, become limited, but for laser and spark, they have almost the same amount as the initial state, and which give you a lot of NOx. If you look at the ignition, actually all the three are very similar. There's not much big difference. The major difference is during the pulse, plasma already consume a lot of ammonia to reform them into nitrogen and hydrogen. Okay. Okay, so that's about ammonia, and we did a 0D parametric study. But this is an OpenFOAM webinar. We are more interested in CFD, so we want to go towards CFD. But it's very hard to do CFD for PAC because we have a couple of the physics, and more importantly, we have a very wide range of timescales. The discharge and the plasma timescale can be 10 to minus 13 to 10 to minus 8 seconds, while combustion kinetics and turbulent flow is normally 10 to minus 6 to 10 to minus 4. So this is like 9 orders of magnitude difference. Okay, so we want more physics. We also want affordable CFD. So these two contradict with each other. There are several solutions. First one is we want to do detailed, very detailed plasma part, but ignore everything else. So it's the 0D solver. That's what we did for the ammonia case. The other way is we want a little bit dimension and fluid, so we can make it 1D. That's my PhD work at Georgia Tech. And you can also extend it to 2D to do some laminar flow discharge. And there's some paper about it, and it's very expensive. You cannot do 3D, you cannot do turbulent case. 2D laminar is the best you can do. If you want to do 3D and turbulence, currently the only feasible way is so-called phenomenological model. So this phenomenological model was invented in France, EM2C, the central Paris. And the basic idea is a little bit similar to the 0D model. For the input energy, you can distribute them into 3 parts: the ultra-fast dissociation of species, ultra-fast heating, and the vibrational excitation. And the vibrational excitation will eventually relax to translational energy, which give you the slow heating. Okay, so the governing equation, we still have the Navier-Stokes, the momentum equation, we have the energy equation, but you have more terms to represent the enthalpy change from the plasma chemistry, the fast heating, the slow heating from the vibrational to translational relaxation. And to capture this process, this VT relaxation process, you also need to introduce vibrational energy. And this is the source. The plasma give you vibrational excitation. This is the sink. The VT relaxation give the sink. And of course, the species equation, but you need to add the plasma term. Okay, so we have more details here because of the time, I probably won't talk too much, but one thing I want to mention is this phenomenological model assume a waveform for the power density. You basically need to give a power density as an input file to the code such that this phenomenological model can work. And they assume this power density function does not change with time, which later I will show that's often not the case. Okay, so we basically developed this model. The model is not invented by us, that's from the EM2C, but we developed it in the OpenFOAM. Just like the VLE solver, we did in both the low Mach version and the fully compressible version based on row pimple form and row central form. Okay, and one thing is the molecular transport become important. So the default OpenFOAM use unity Lewis number, unity Prandtl number assumption. So we couple the Kantara to provide the detailed transport property. Also, Kantara give us the CVOD to handle the stiff chemistry. And by the way, our Kantara coupling is already posted on GitHub. Anyone can go ahead to download and use it. So with the solver, we can simulate some interesting case. This is a 3D ignition kernel evolution with plasma. So we have a laminar case and a turbulent case. Turbulent case, we basically enforce isotropic homogeneous turbulence. Okay, so in the plasma ignition, initially, if I play this video again, initially, you can see a shock wave, weak shock wave generated by the plasma discharge, and the shock wave will go outside, first become acoustic wave and then go outside. You can often form this interesting toroidal shape in the laminar case. When you have turbulence, turbulence will basically convecting radicals and vibrational energy and the temperature hotspot away from the center of the domain to the other region. This actually is a destructive process. As you can see the result here, the laminar case, we can get a successful ignition with this toroidal shape. Turbulent case, when your turbulence intensity is high enough, with the same plasma input, you can get ignition failure. The reason is to get ignition, you need a focused heat radical all in the center of the domain, but turbulence basically push many of them away, give you ignition failure. So for practical problem, we might need a stronger plasma source, plasma input. So the energy consumption will be higher, but hopefully still relatively low compared to the traditional technology. For plasma ignition, a very interesting work did by Lefkowitz and Umbrella was this effect of pulse frequency. And what they found is depending on the frequency, your plasma discharge pulse can have fully coupled mode, partially coupled mode, and decoupled mode. The coupling means basically each pulse, each discharge pulse will give you some ignition kernel. And if the two pulses are close enough, the ignition kernel can couple together. So we try to simulate this case to get more insight and understanding about it. So we simulated both the fully coupled case and the partially coupled case. The fully coupled case is shown here. And you can see the interaction between the plasma discharge with the preceding kernel results in a strong ignition kernel and successful ignition. And you can wait the simulation to go further and you can see whether it's going to die out. You can also check the reaction rate, the heat release rate plot, which we are not showing here, but that can tell you whether it gives a successful ignition. If you go back to their experiments, fully coupled case is here. The ignition property is almost 1. So we successfully capture that. Now let's see the other case, which is partially coupled. Partially coupled case, you can clearly see the difference between the two ignition kernel. They are in touch, but they are not merged like the fully coupled one. And in this case, you have more volume of onboard mixture exposed to the individual kernels, but have very little interaction of the new discharge with the previous kernel in terms of the radical and the temperature. You see, for example, temperature, these two are already disconnected, so they cannot help each other. So eventually we get a failed ignition as the simulation tells us. And this also agree with the experiment. If you go back to see the experimental data, the partially coupled cases here, the ignition probability is less than 0.2. So in most cases, you should get a failure, which we indeed captured. Okay, so that's about the phenomenological model. We also try to improve it. The way we can do is to do a more detailed plasma modeling. But we cannot do it for the full system. We assume we only need to do the detailed plasma modeling for air. So we have air chemistry. We do a 2D case, and we can introduce the photon ionization. And of course, you solve the boson equation to get the real electric field. This is using the Pascal code available from this website. Okay, so what you can see is the electric field is actually not the same through time. So recall that the phenomenological model, you need to assume the electric field, the power density are always the same at any time, but that's not the case, as you can see from here. So, and this is the power density. You can also see it's very different. It's always starting from the 2 electrode, and then you have this so-called streamer start to grow. Eventually, the 2 streamer will connect each other to that so-called streamer connection, and then it becomes relatively stable. The phenomenological model assumption is only valid after this streamer connection. But if the process before that is important to you, then the phenomenological model have issue. So the assumption may not be applicable, and the maximum power density can be 3 orders of magnitude higher than the constant power density in the phenomenological model. So our current plan is we can use Pascal to do a detailed 2D simulation to get the time variation of the power density. And we save that as input file to the phenomenological model. So we're already doing that. So this is the Pascal results. You assume it's axis symmetric, you rotate it, you map it into the 3D CFD domain for the phenomenological model to use. And you can see this start from the electrode, and eventually you get a streamer connect with each other. And then we can do the ignition simulation again. And you can see the ignition kernel actually starts with the electrode rather than near the center. The original phenomenological model will not capture start from the electrode. And it can evolve like this. So you can see it's highly non-uniform. And it's very important, especially in the early phase, to capture this non-uniformity of power density and the time evolution of the power density. Okay, so that's all my talk. I also want to make an advertisement of the postdoc opening in my group about this turbulent plasma assisted combustion simulation. So please help me advertise it and let anyone interested in the position to apply.